We're often told that artificial intelligence is a black box, a system that, well, it gives us answers, but its inner workings remain a complete mystery. But what if we could actually peer inside that box? Today, we're going to move beyond simply asking what a model decides to understanding something far more profound, how it thinks. So imagine you're applying for a loan. An AI model comes back and says your income is the number one most important factor. Okay, that seems straightforward enough, right? But what does that actually mean? Does having more income always help your chances? Is there a point where it just stops mattering, and does it have the same effect on everyone? You see, the answers to these questions, that's where the real story is. For a long time, we've had to rely on pretty simple metrics, but they only really tell us part of the story. So right now, we're going to move on from just asking how much a feature matters to truly understanding how it shapes the final decision. Looking at this, income is the clear winner. It carries the most weight, no doubt, but this chart is totally silent on the nature of that relationship. It's a bit like knowing the most powerful ingredient in a recipe, but having no idea if it makes the dish sweeter or saltier, or if its effect completely changes when you mix it with something else. So what this really tells us is that we need to move from this simple idea of weight to a much more revealing concept, the concept of shape. It's the shape of a feature's influence that tells the true story, and that's exactly what we're going to uncover. So how do we actually see this shape? Well, our first tool is something called the partial dependence plot, or PDP for short. Think of it as our way to see the average story of how one single feature affects the final outcome. The process behind it is actually quite elegant. Imagine we take one person from our data. We'll call her Anna. We keep every other detail about her exactly the same. Her age, her credit score, all of it, but we digitally alter only her income. So first, we set it low, say £20,000, and we get a prediction from the model. Then we nudge it up to 25,000 and get another prediction. We do this over and over across the entire range of possible incomes. What we end up with is Anna's own personal prediction curve. Then, and this is the crucial part, we do this exact same thing for every single person in our data set, and we average all of those individual curves together. And the result of all that averaging is the PDP. It's one single line that represents the average story of how income affects a loan prediction across everyone. It's meant to capture the overall trend, the big picture. And reading this line is pretty intuitive. If the line is rising steeply, it means more income has a strong, positive influence on getting that loan. If it starts to flatten out into a plateau, that tells us there are diminishing returns. After a certain point, more income just doesn't help you much more. And of course, if the line were to fall, that would mean it has a negative influence. The shape tells the story, but the average, as we all know, can be well deceiving. What could it be hiding? To find out, we need a new tool. It's called the Individual Conditional Expectation Plot, or ICE. This is what lets us peek underneath that single average line, and this is the question that should really give us pause. What if the model behaves one way for one group of people and a completely different way for another? An average would just smooth over those critical details, hiding something incredibly important right there in plain sight. So let's put them side by side. The PDP, that's the summary. It's one single line showing the average effect. The IC plot, on the other hand, gives us the details. It doesn't average anything at all. Instead, it plots the individual curve for every single person. It's the big picture versus the often hidden truth. Now, if you look at an ICE plot and you see all the lines running more or less parallel to each other, well, that's good news. It tells you that the feature, in our case, income, has a pretty similar effect on everyone. The model is behaving consistently. But this is where things get interesting. When the lines start to fan out, or worse, even cross each other, that is a dead giveaway that the average was, in fact, hiding the truth. It means the effect of income depends on something else, some other characteristic of that person. This chaos of lines can reveal something really profound. For instance, we might discover that the model uses income very differently depending on a person's age. For younger applicants, a higher income might dramatically increase their chances of getting a loan. But for older applicants, it barely moves the needle. That single average line from the PDP would have completely masked this inconsistent and, frankly, biased behavior. And look, this isn't just some abstract academic exercise. This is precisely how we debug AI models in the real world. It's how we audit them for fairness. It's how we can detect and then challenge potentially discriminatory or unfair lending practices that would otherwise stay completely invisible, locked away inside that black box. Okay, so we've seen how a single feature behaves. But in reality, features rarely act alone, do they? They interact, so what happens then? Well, for that, we can expand our PDP approach. This gives us what's called a two-way PDP, and it's often shown as a heat map like this. So in a weather model, for example, a high temperature on its own might raise the risk of a storm a little bit. Same for high humidity, but it's the combination of the two, high temperature and high humidity together, that really sends the risk prediction soaring. This kind of visual makes that hidden interaction completely obvious. So after all that, where have we ended up? We've taken a journey from a simple, almost misleading bar chart deep into the intricate logic of the model itself. We've effectively transformed the black box into an object of genuine scientific inquiry. We saw that the partial dependence plot is our starting point. It gives us the clean, simple summary, the average story of how a feature works. But then we saw that the ICE plot gives us the often messy, but far more important truth hiding just beneath that summary by revealing the individual behaviors and the potential biases that the average can so easily hide. Ultimately, what these tools allow us to do is to shift our fundamental question. We can move beyond simply asking, does this model work, to a much deeper, much more essential inquiry. How does it think? And answering that question, that is the absolute key to building artificial intelligence that we can genuinely understand and ultimately trust.